Welcome to the next video, everybody. Today we're going to be talking about the local conditions and the associated computations that go into the proof of Fermat's last theorem in just a little bit of detail. Okay, so first of all, let's fix a finite set, sigma of primes including infinity. Let's let P be an odd prime, and let's let R be a finite ring with order that's a power of P. We'll let X be add zero row, so that's the action on the trace zero matrices, where row from GQ to GL2 of R is some two-dimensional odd representation. Okay, we'll just note that oddness is equivalent to row of C being similar to matrix 1, 0, 0, -1, where C is complex conjugation. Okay, let's define our local conditions as follows. For a prime L not in sigma and not equal to P, big L sub little l will be H1 of GL mod IL add zero row to the I sub L. So the unramified classes. Okay. Big L sub little l will be H1 G sub L add zero row. So it's kind of everything. It's the full H1 if L is in sigma and not P. And we will specify big L sub P later. What we're essentially asking or setting up with these definitions is that there should be as little ramification at primes not equal to P and outside sigma as possible when we move to infinitesimal deformations. Okay, and at primes not equal to P in sigma, we allow arbitrary ramification. We allow things to get as bad as they want. Okay, what happens at P is something that we have to control more carefully. Okay, so the goal is to sort of get a handle on the product formula with this setup. And by the way, why are we considering add row? Remember, that's the trace zero matrices, and those correspond to infinitesimal deformations with fixed determinant, which will be something that's important in the proof of Fermat's last theorem. In fact, you've already seen it in my summary of the proof so far. Okay, so we're going to seek to use theorem 2, which is the product formula. And so most of the work is done trying to calculate these factors in the product. The factors, cardinality of big L sub little l over cardinality of H0 G sub L add zero row at various primes. And here's what you find. By lemma 1, the factors for the primes L not in sigma that aren't equal to P are just 1. That's an easy one. Okay. The factor at the infinite prime is also easily found. So the absolute Galois group of R has order 2, and add zero row has odd order. And so H1 of G sub R add zero row is 0 by coprime vanishing. And so L sub infinity, which is a subgroup of the trivial group, and so it must be trivial. Let's assume without loss of generality that row of complex conjugation actually is just row 0, 0, -1, using a remark I made above. Then row of CA, row of C inverse equals A if and only if A is diagonal. And so H0 G sub R add zero row is just the size of R, just the cardinality of R. If you combine all this information, you find that the factor in the product at the infinite prime is 1 over the cardinality of R. Okay, so most of our factors, so just outside sigma and not equal to P, our factors are all 1. At the infinite prime, our factor is 1 over cardinality of R. How about primes L in sigma that aren't P and which aren't infinity either? Okay, if you go, I didn't give you the proof of proposition 5. This was the whole growth of the Selmer group proposition from last video. But if you look at the proof, you find that the size of H1 G sub L add zero row over the size of H0 G sub L add zero row is equal to the size of H0 GL add zero row star. Okay, and so we get this is exactly what we needed to compute in that case. And so here would be our factor. Okay, so the only thing missing is what happens at the prime P. Well, we'll consider possible local conditions at P. First, we'll look at ordinary representations. Let's suppose for a suitably chosen basis that row when restricted to G sub P has the form psi1 epsilon star 0 psi2, where psi1 and psi2 are just unramified characters with values in R cross. That essentially what I mean is these characters on GP are trivial on I sub P. They're unramified characters. Okay, and epsilon is the cyclotomic character, which gives the Galois action on sort of P power roots of unity all at once. Okay, we'll call such a representation row ordinary at P. This is a definition I've given before, quite long ago by now, actually. And then we'll look at W0. That'll be the additive subgroup of add zero row given by matrices of the form 0 star 0, 0. So they're like sort of strictly upper triangular. Okay. So 2 lemmas, and then we'll call it a day, and we'll pick up tomorrow part 2 of these computations. So lemma 2, turns out GP, so the decomposition group at P, acts on W0 by multiplication by psi1 epsilon over psi2. This is just a simple calculation that can be found in CSS page 114. More importantly, lemma 3, The size of H0 GP W0 star is the same thing as the size of R mod psi1 psi2 times frob P minus 1 all times R. Okay, and really this follows quite quickly from lemma 2 and is proven in CSS on page 114 along with lemma 2. Okay, so next time we will define big L sub P in one of two different cases, basically depending on whether or not it's gonna, in Weil's proof, it depends on whether or not he's working with ordinary elliptic curves or super singular elliptic curves. But we'll have L sub P defined in two different ways in two different cases. And then we'll have sort of all of the product formula factors computed by that point. So thanks for watching, and I'll see you then.